We will now solve problems using the concepts of specific heat and latent heat. Now remember the major difference between specific heat and latent heat. For specific heat, a change in temperature is involved. For latent heat, there is no change in temperature involved. So during a temperature change, the quantity of heat absorbed or liberated is mass multiplied by specific heat multiplied by the change in temperature. On the other hand, the amount of heat absorbed or liberated during a change of state is mass multiplied by either latent heat of fusion or latent heat of vaporization. Alright, let's start with example 1. A solar home contains 10 to the power 5 kilogram of concrete of specific heat capacity 1 kilojoules per kilogram per Kelvin, 1000 joules per kilogram per Kelvin. How much heat is given off by the concrete when it cools from 25 degrees to 20 degrees Celsius? Now here we need to find the quantity of heat given off when the temperature changes. So it involves only specific heat. Alright, let's pick the data. Mass of the concrete is 10 to the power 5 kilogram. The specific heat of that substance is 1000 joules per kilogram per Kelvin. The change in temperature delta theta is 25 minus 20 is 5 Kelvin. Now remember, the temperature interval 5 degrees Celsius is the same as 5 Kelvin. Although their starting points are different, the intervals are the same in Celsius and Kelvin. Okay. The quantity of heat absorbed in order to achieve this is, in order to achieve a change in temperature, is mass times specific heat times change in temperature. We know all those values. Mass times specific heat times change in temperature, and that is 5 times 10 to the power of 8 joules. In fact, there are cold regions in the world where substances of very high specific heat are heated during the time electricity is very sparsely used. You know that there are peak times for electricity and there are dull times. So in England, you can actually buy electricity cheaper at certain time. That means if you use that cheaper electricity to heat substances that have very high specific heat, and you are storing that heat during the evening hours when the electricity is very costly, you can turn off, and the heat that you stored during the day will now heat your home. You see, that object that has increased its temperature will now throw away heat, will actually warm up your house. A very economical way of heating homes. Alright, let's look at a principle of calorimetry, a very important principle in doing heat calculations. Now what is calorimetry? Calorimetry is the science of calculating amount of heat lost or heat gained, heat absorbed, heat liberated, and so on. Now when hot objects are mixed with cold objects in a thermally insulated container, the hot objects will lose heat and cold objects will gain heat. Is that right? And if the system is insulated from the surroundings, we can make a conclusion. When thermal equilibrium is reached, we can say that the total heat lost by the hot objects will be equal to the total heat gained by the cold objects. We assume here that no energy is either given out or gained from the surroundings. You see, heat exchange takes place in a thermally insulated environment. When that happens, the amount of heat lost by hot objects will be equal to the amount of heat gained by the cold objects. If you practice this, you can solve any problem in calorimetry. As long as you know how to calculate the amount of heat lost or gained. The amount of heat lost or gained when there is a change in temperature is mass times specific heat times change in temperature. On the other hand, the amount of heat gained or lost during a change of state without a change in temperature will be mass times latent heat. All right. Now this principle can be used to solve for unknown quantities. And this insulated container that we use in the lab, if you come to the campus to do a lab in this kind of subjects, we will be using this thermally insulated container to perform the experiment. And such a container is called a calorimeter. A calorimeter. Now here is a typical example of a calorimeter. A calorimeter has a housing. This is the housing. And inside, this is where we allow heat exchanges to take place. This is the isolated or insulated container. You can see there's an insulator there which will insulate this from the surroundings. And you use the lid like this, and you use, this is called a stirrer that can be used to stir. So this is part of the calorimeter, and in order to measure temperature you can insert a thermometer through this hole. So this is a thermally insulated container, and this is called a calorimeter. And most of the experiments that we do in the lab on heat exchangers are done in a calorimeter. All right, let's do a problem.